Hello, this is Concrete Path. Today's lecture is what you call as cables. When you apply load, when you apply load on the cable, that they resist the load. They resist the load by developing an internal force of axial tension only. So they develop only axial tension. Axial tension they have. They only resist the load because of only developing axial tension. So their use we can have in suspension bridges. We can have cable stayed bridges. We can have cable car systems. Like that of gondolas, and we can also have those transmission lines, power lines, transmission lines. So, but they resist the load by developing axial tension. So, in our syllabus, we will be having that cable is subjected to one is your point loads, concentrated loads, and second one is that what we have uniformly distributed load. So when we say we are studying cables, we have some assumptions here. Assumptions in force analysis of cables. What are the assumptions we have in the analysis for your forces? That's axial tension in the members of those cable members. What is the assumptions we take for calculating the axial forces we have, and force analysis of those cables? So first one is that we say the cables are perfectly flexible. They are perfectly flexible. And second one is that we say they are inextensible. Now, by the first assumption, we say cables are perfectly flexible. That means there is no development of bending moment, shear force, and no compression. So if there's any cable, let's take any thin wire. Let's say any thin wire. You apply tensile force, it will have some resistance. That means only axial tension it can develop by resisting that change in length. But if you try to apply compressive force on this cable or a thin wire or that thread of fiber, so it won't resist anything. It would go in a curved fashion. Or similarly, if you try to rotate it, apply bending moment, so it won't have any effect. So there won't be any development of bending moment. So this is the case. But if you actually but in the general case, when we design some system like that, a bridge, so there the cable is not like a thin wire. The diameter of that, it's some sort of those lots of strands wound together to form a bigger diameter. So cross section is bigger. So area cross section increases in the actual case, and we have some modulus of elasticity also. So it can have bending moment developed here. We can have shear force. We can have bending moment. We can have compressive forces also. So this is the assumption that if the wire is very thin, we can assume that your cable is perfectly flexible. Second one is that we say they are inextensible. That means they are not going to be stretched. So that means strain equals to 0. So by this concept, we say we can apply the concept of rigid body analysis of forces. So by that concept, we say we can solve the forces by assuming the body to be rigid, and based on that, we say the force in the member would remain constant, force in the segment would remain constant, and it won't have any effect based on the rigid body concept. So this was your inextensible. That means that that the length remains constant before and after. Length is constant before and after the application of load. Before and after the application of load. Now, we have one theorem that we call as general cable theorem. General cable theorem. General cable theorem. General cable theorem. Let's have that. General cable theorem. So for this we make a mahole. Let's make mahole. Let's make a mahole. We say we have two supports A and B, A and B. We have two supports A and B, and the cable was initially between these two supports, and they are at a level difference. They are at some level difference. So they are at some level difference. We say they are at some level difference. Let's say that the horizontal length between the two supports is length L. So let's say the horizontal distance between the two supports equals to length L. And there's some theta developed, and we call this AB as AB dashed line segment as a chord line segment. That is a dashed line connecting the two supports, but they are separated by some that elevation. We have some delta between the two, delta vertical. So if you join the two by a straight line, that thing we call as a chord AB. So, and we have some theta with respect to that. We say with respect to that horizontal, we say we have some theta between the two. So that's some theta. And I would say, what is this vertical here? What is the vertical here? Can you get that? Tan theta? I would say that is equals to L tan theta. L tan theta. Now the wire, now the cable is cable would have been in this fashion, some sort of cable would have been there. But we say that we are not keeping it free. We are applying some loads. We are applying some loads. If we apply some loads, it is not going to be in that same fashion. So to maintain the force equilibrium, its geometrical configuration changes. When you have a wire and you are applying a concentrated load at different points, its configuration gets changed to maintain that equilibrium of forces. So it changes its configuration. Then we say if there are point loads, if there are few point loads, initially the segment would have been in this way, that it's hanging under its self weight. It's hanging under its self weight. So, but if you are applying any load, particular load, at that location, we say from this support to this point, we can join them by a straight line, and after that we can have in this fashion we can have it in this fashion. This is the profile it develops because of concentrated loads. Similarly, if you have two loads, if you have two more loads, let's say the length was A 3A, total length was 3A horizontal, then you apply one load here, one load here, then the profile would get developed as in this fashion. The profile gets developed in this fashion. A straight line segment, such that delta here is equals to delta here when the load was P and P, if the load is same P. Now, if I apply load of 2P and P, let me apply a load of 2P and P. If I apply a load of 2P here and a load of P here, the profile that gets formed for these cables would be in this fashion. It won't be symmetrical. I would say it would have some delta here that's more as compared to this one, and after that it would have some sort of configuration in this fashion. So you're applying 2P here, you're applying P here in this fashion. So your that cable takes the shape some sort of line segments for the point loads. Similarly, now if you're applying few loads, so the profile would not be in this fashion. I would say profile gets changed. Profile would get changed. Let's make that. I would say profile would be some sort of straight line segments. Let's have few segments. We want to have a general derivation of that. What's your general cable theorem means? Let's say there are few point loads. there are few point loads, and because of that your diagram looks like this. That cable takes this shape. Let's say there was some load of P1, there was some load of P2, here we have some load of P3, and so on and so on. We can have n number of loads, and let's say the loads are Pi. A particular load of Pi is at xi from that support A. We say that any particular load is at a distance of x from your support A. So that's your first condition. That after that we say you take any point anywhere. Let's take any point. Let me take this point. This point is at a distance of x from the support A. This point is at a distance of x from the support A. So this point is at a distance of x from the support A. I would say, I would call this vertical distance as A. This point B, vertical distance of that point B with respect to the horizontal line from the support A, that we call as A. And one more thing is that above that point that is up to that chord line, up to that chord, we can call it as YC dash, YC bar. We can call it as let's call it as Y bar, not YC bar. Let's call it as YC Y bar. Let us call it as Y bar. Let's call it as Y bar. So there we have some Y bar, and you can get that what Y bar is. Y bar is actually, I would say, Y bar is vertical distance of point P to your chord line. Add that x location from support A. And similarly, you can write what's A. It's with respect to horizontal line from A to that point B. So you got these two. And one more thing is that what is the total value here? Can you get what is the total value here? What is this Y bar plus A? What is this Y bar plus A equals to? Can you get what is equals to? This total was equals to L tan theta for the length of L. And if I have that similar triangles, if I have some theta, if I apply that same by similar triangles, I would say this one would be equals to x tan theta. Let's keep these datas on a side, and till now we would get some mahol. We'll make some mahol. So once we made the mahol, we would say let's go for that force equilibrium and moment equilibrium. Let's go for those, and we want to see what's the values of those reactions, etc. Let's go. If I say that summation of moments about P equals to 0, can you tell me what are the reactions we have? What are the reactions we have? If we have these supports, we say that it's both are pinnet supports. That means it's providing a reaction of A, and this is providing a reaction of HA, and from this side also it's providing a reaction of HB, and it's giving a reaction of B. Now we say that by the force equilibrium of that, summation of FH horizontal forces equals to 0. Since your loads of PI, they are vertical, that means no horizontal force is there, external. So we say your horizontal A equals to horizontal B, that equals to some value of H, and both are in the opposite direction. One is in this way, next one is in this way. So once we apply that, now second is that if you apply summation of moments about point B, I would say your reaction of A, that's clockwise about point B into length of L, A into L, clockwise positive, and your horizontal of H at point A, that's also clockwise, H into, and what is the perpendicular distance between that A and B? Is that L tan theta? Is that L tan theta? Your H is acting here. Your H is acting here. Is that L tan theta? Can you tell me this is L tan theta? Is this L tan theta? Yeah, it is L tan theta. So we can have that L tan theta. You can write H times L tan theta. And they are both clockwise. But because of the loads, can you see? Because of the loads, they are acting anti-clockwise about the point B. They are acting anti-clockwise. Can you see that? So we can write that minus times effect of those loads. If you write that minus times and you transfer that effect, all the loads have anti-clockwise fashion of that. Then if you write that minus times some summation of all those moments about point B, and that equals to 0. If I say that what is this summation of MB, I would say this is the net value of that effect of the loads, effect of those loads, effect of the load. This is the value. I can say this is the summation of moments of because of the loads pi about point B, Can we say that it is the effect of those loads? This one would contribute some moment, this one is contributing some moment, this one is contributing some moment, and finally we say this is the summation of all those loads, summation of all those moments because of those different loads about that point B. We call that as summation of MB equals to, then finally if I write that AL plus H times L tan theta equals to summation of moments about point B. Let's keep it as equation 1. Now we do one thing. What we do? Now we take any general section. Now we are going to take any general section now. We are going to take any general section. If we take any section, if we take any particular section, I would say let's take any section at a distance of x. That's why we made this mahal initially. If we take any section x, let's take any section x, that's from A. That section is at x from A, at x length from A. We have this one. Now we want to see what is the moment here, because we say your cable, by the assumption that it is perfectly flexible, that means the bending moment is 0 at all sections of the cable. That's what the perfectly flexible assumption means. That means it cannot have any bending moment anywhere in the cable. So we say bending moment at all sections equals to 0 by the assumption 1. Bending moment at all sections of cable equals to 0. One is your moment, summation of moments about any section. That's always 0 because that is equilibrium. You have to maintain equilibrium as a civil engineer. You have to maintain the equilibrium. That's your already case that summation of all those moments should be 0. But one is that bending moment at every section in the cable, it's 0 if the cable is perfectly flexible. That's what we are talking about. Now, if I cut any section, that section, I would say we have some general configuration here, some sort of we have these P1, P2, P3, and up to that section X, we will say there was some moment, bending moment Mx, and that equals to 0. Now, if I apply that summation of moments at that section equals to 0, I would say we have some reaction HA and we have some reaction of A, and we can get something from here. Now, if I apply that summation of moments at that section equals to 0, I would get that, I would say your reaction of A into length of, how much length is there up to that section X? Is that X? A into X clockwise about that section, clockwise positive. And similarly, your horizontal into X, clockwise rotation about that point X, horizontal into X, A into X. No, not H, times X. It's vertical. We have to get the vertical displacement, vertical distance. That's what you can think of vertical displacement distance is that. So if I say that horizontal H is acting here, and it's having some relative vertical distance up to that point, and it's equals to A. So I can write H times A, moment of H times A clockwise, H times A clockwise. Can we write that? H times A clockwise. I think we can write that. H times A clockwise. And all the other loads, they contribute anti-clockwise moment. Let's call it as that minus times summation of, let's write that as summation of moments up to that mx, up to that x equals to 0. Can we write this equation? Because moment at x, bending moment at x equals to 0, and we have only your reaction of A, reaction of H, and all other loads. These are your external loads, Pi. Because of these Pi up to that x, from the left of that section x, we are saying that this is the summation of mx. That is the effect of those loads, moment contributed by all those loads that are on the left side of that section. That's why we write this one as your summation of mx. So you can write this one. This is the moments, summation of moments of all loads from left of that section. All that loads pi from left of that section, on the left side of that section, on the left side of section x. So we can write it in this way, that ax plus ha. And can you tell me what is the value of a? Earlier we have made one equation of a. We have made some equation of a. Can you see anywhere what is the equation of a we have? What is the equation of a we have? I would say value of a equals to x tan theta minus y bar. Total was here. Total here was x tan what you call as x tan theta minus y bar. Yeah, a equals to x tan theta minus y bar. Let's have that value, x tan theta minus y bar. So I can write a equals to x tan theta minus y bar. So let's have a different color here. Let's have a different color here. I can write x tan theta minus y bar, x tan theta minus y bar, and then I write minus times summation of mx equals to 0. Now, if I try to compare this one with the case one, do you think any relation is there with these two? I would say here is a function of a times l and hl tan theta, and here we have a times x, h times x tan theta. So I can keep it in that fashion. Let's have that in that fashion. So if I write it in terms of a times x plus what you have h x tan theta. So I can have this value on one side, and similarly I can write that one more thing, that one is your h times y bar. That's negative, and if I keep it on the other side, I can get positive value h y bar. And one more thing is that we can get summation of mx. So we got this equation. Now if I want to convert this part, in terms of this one, in terms of x, so I have to multiply this equation by x times. So if I multiply equation 1 by x by l, if I multiply this factor on the equation 1, I would get a equation that looks like that, x by l of al plus h times l tan theta equals to x by l and summation of moments about point B. So I got this equation. Now if I simplify it, I would get I would get it in terms of this one. I would get a into x plus h times x tan theta, and that equals to x by l summation of mb. Now if I have this one, if I substitute it in this equation, what I can write now? What do you think? What I can write now? I would be writing that this is equals to, from this part I can write this is equals to x by l summation of mb, by doing that, substituting that value here. So once I got it, so I can still do one thing. If I keep it in terms of hy now, let's keep it in terms of hy bar. Hy bar equals to then x by l summation of mb minus summation of all those moments up to that point x, because of the loads. This summation of mb and summation of mx it's all because of the because of those loads of point loads of pi about the point B. Yeah, this was your pi effect of those loads, moment developed because of those loads about point B, and this was your moment of those loads pi up to the point x, and it was about point x, it was about section x. So then we have this factor of x by l, and we got this equation. Now we are going to do one thing. Now. Let's have a general simply support beam. If I have a general simply support beam subjected to same loads, we have these loads P1, P2, P3. We can have any number of loads. Let's keep only these three loads P1, P2, P3. P1, P2, and P3. Let's have these P3, P1, P2, P3. They are at X1, they are at X2, they are at X3 from the what you have from the support from the support A. Then we say, can you calculate that? Can you calculate that? What can you calculate the reaction A? Can you calculate the reaction A? I would say if I apply that summation of MB equals to 0, that summation of moments about point B equals to 0, I would get that A into L, because your H, it's on the same line. It's that beam on both supports are at the same level. I would say H into 0. So A into L, that's equals to the moments contributed by all those loads. The moment contributed by all those loads. Summation of MB, and so I would get this equation. Can I get this equation? I would say I can have that in this fashion. I can say, I would show you that. If I write that A into L is your clockwise, then we have some minus times P1 L1 minus P2 L2 plus minus P3 L3 equals to 0. Then I have this value. I can name it as that summation of moments about point B because of the loads in the simply support beam. Where this one is your summation of MB in the simply support beam. So I got this. If I write what is the value of A, can you tell me what is the value of A now? I would say value of A equals to summation of MB divided by L. Let's keep it for now. Now I take any section. Let's go for any section X. If I take any section X, I would say what is the summation of moments at that section X. If I cut the section, there might be some shear, there might be some moment, bending moment mx. In the beam, there is in the beam, the difference between that cable and the beam, we are saying bending moment in the cable at any section is 0. But in the beam, it can be 0, it cannot be 0. There might be some moment at any x. So this is the difference here. So if I take that section, I would say, what is the moment at any x? If I write the summation of moments about that section equals to 0, I would say I have that A into some x length, A into that length of x, and there is some moment contributed by some loads P1, P2, P3, because I take any section, general section. So there would be some moments because of the, there might be some general moments because of those loads. I can call it as summation of mx, and there is some moment here also. There is some moment also here that we have, that we can call as minus times mx equals to 0. The difference between this one and this one, it's because of those pi loads, because of that pi loads, and this is at the section. When you cut the section, this is internal bending moment at that particular section. It is because of that beam, we have some section, and at that section, if you cut that, there is some internal bending moment developed. This is the difference here. Don't get confused. So okay, so if I now write that, what's the value of A into x, that is equals to mx plus summation of mx. Now if I write that in this way, let's write that, what is the bending moment at any x? What is the bending moment at any x? What is the bending moment at any x? This is the bending moment at any section x in the simply support beam. In the simply support beam, let's write it in this English way, such that you can have understanding. Mx is the bending moment at any x, section x in the simply support beam, and that would be equals to A times x minus summation of mx. A times x minus summation of mx. And if I substitute the value of A, equals to summation mb by L, I would say summation mb by L into some factor of x, then summation of minus times mx. That is your moment at any x. So I got this equation, and initially I got one more equation in terms of that. Initially I got equation when we studied that cable. So I got this equation, x by L of summation mb minus summation of mx. Here we also got x by L of summation mb minus summation of mx. So if you see those two equations, we have this part, they are also here, they are also here. So I got that mx in simply support beam is equals to h times y bar at in cable. Do we got it? That bending moment, this is your bending moment at any section x in the simply support beam, that is also equals to, that's also equals to h times, that is h times y bar in the cable. So where your h is the horizontal component of the reaction, horizontal component of the tension, horizontal component of that tension in the cable, horizontal component of cable tension. In the cable, there is development of axial tension, and it may have components along x and along y. Then finally there would be some resultant, or that's tensile stress, tensile force. So we say it's the horizontal component of the cable tension, horizontal component of cable tension. And if you multiply that y, what is this y bar? We had two supports, and when I joined them by a straight line, we call that as a chord. Then the profile was some sort of in this way. Let's say the profile was in this way. Then we take any section x, we take any section at a distance of x, particular section x. There was a point P. I said that the point P, you take any point P, general point, not at the same level. Let's don't take any. Let's take a point at any different level to make a understanding. So the horizontal level was this one. This was the horizontal line from A. Then I take any point. Let's take this point P. Let's call this point as P. Then I said that this distance equals to A, and the y bar was this one. Y bar was this one. That from the point P to the chord line, that this vertical distance was equals to y. If you take any point P here, I would say this distance equals to y. If you take any point here, I would say this distance equals to y bar. So it depends on the value of that y bar, So this is your y bar in cable at any section x, at x. So you know that y bar, what is y bar? So this is the general cable theorem. The statement we can write, the statement from this equation we can write for the general cable theorem. General cable theorem says that product of horizontal component of cable tension, horizontal component of cable tension, that is product of horizontal component of cable tension with what you have, that y bar. That is the vertical distance. We know that is the vertical distance of that particular point, with respect to chord line at that section x, chord line AB at that section x, and that is equals to bending moment at any section x, in the simply support beam having the span of same L equals to, that means L should be same for the simply support beam and the cable length along the horizontal. This was your general cable theorem. Let's go for a problem that we have. The first problem, and it's very simple, not a big task, Let's go for the first problem. It's saying that we have a cable of horizontal length equals to 400 meter, and delta, that's that vertical distance between the two supports, that's the elevation difference between the supports, that equals to 10 meter. And we need to get at what particular load we have largest sag at what or which particular load, at which load. That means at what location we have largest sag, under which load we have largest sag of that cable. Let's have that general general profile. I would say this is the profile that has some sort of developed. And after that we can have in this way also. So let's say this is your B, support B. By this dot we are showing that it's a that hinged support, so it's having some reactions H and that vertical horizontal A reaction and H reaction. Similarly B reaction and H reaction. So you got this one, and I would say the delta elevation difference between the two is 10 meter. So I would say there is some line from the point A, there's some vertical, there's some horizontal line from the point A, from the support A. Let's say this one. Let's say this is your that horizontal line from the point A, from the support A, and the delta here is equals to 10 meter. This is your 10 meter. Now, because of some load P1, the load of P1 equals to 300 kilonewton, and there is one more load here that equals to 150 kilonewton, one more load of 300 kilonewton, and here we have some 1000 kilonewton, 1000 kilonewton, and the horizontal distance between the between those loads is equals to, let's have that horizontal distance also, and this distance I would say this is 80 meter, this is 80 meter, 80 meter, and this one is your 60 meter, and this one is your 60 meter, this is your 80 meter, 60, 80. After that we have 120 meter, such that total length is 100, and that 400, horizontal length is 400. Okay, you got it now, you got it. Now you need to get where is the largest sag. So sag is the, if I say what is the sag, I would say from the chord length up to that point P, that's your sag, that's your Y. So Y, you can say Y is also sag, Y bar is your sag. So if I have that chord also, if I make a chord here, let's go for the chord. If I have that chord line AB, chord, then from that I would say, now let's remove this one now. Let's remove this one now. Let's remove this one. I would say your sag at different levels of those loads, that's different. Let's show that by different color. Let's go for the blue color. I would say this is your this one, this one, this one, and this one. So under the 4 loads we have 4 different sags, and we need to get those 4 values, and out of those, let's say this one is your Y1, this is Y2, this is Y3, this is Y4, or we can name them as A, B, C, D, whatever you can do. So now we need to get, how can you get the values of Y1, Y2, Y3, Y4? Based on the theme that we have general cable theorem, that if you write that equation that Hy bar at any location x, that is equals to bending moment at any x in the simply support beam. If I have this equation of general cable theorem, I can get some stuff here. If I know the value of H, I can then vary the, because your H is not going to vary, H is going to remain constant. H is going to remain constant. If I know the value of H, then I can say for different values of Y and different values of X, then I can get the values of those different Yi. Because I have the section fixed, that is X is fixed, I can know what is the bending moment at that section X, I can get the bending moment at that section X, and based on that I can get the ordinate Y at that location. So this is the profile of that, this is the theme of that problem. How can we go for this problem? So first thing that, let's have that one of the reactions to get the bending moment in the simply support beam. We solved it in the derivation also, that we solved one of the reaction. Let's go for the reaction A. If I got the reaction A, then I go from this side to some x from that A, then I have some that effect of those loads also, so I can get the bending moment at that section X. So let's have that step by step procedure. Let's go for the reaction at A first. We know that this is the final ultimate way to solve that problem, but before that I need bending moment at any x, and for that I have to get the reaction A. Let's go for the reaction A. If I have a simply support beam, let's assume that it's only a simply support beam, there is no horizontal reaction. Let's assume that it's only a simply support beam. So first case is that if you assume that it's only a simply support beam with these loads of, one is your 300, one is your 150, after that we have 300, and one more, one is your 1000 kilonewton, and they are acting at those different locations of 80 meter, 60 meter, 60 meter, 80 meter, 120 meter, and there we have some support B, and we have one more support A. And if I say summation of moments about point B, I would say A into some length of 400. Total length of L was 400, and that equals to effect of these loads, moment contributed by those loads about point B, and that I can say that is 1000 into 120 plus 300 into 200 plus what you have 150 into 260 plus 300 into 260 plus 60, that is 320. Then I can get that value of A is equals to value of A, that reaction, vertical reaction at A equals to 787.5 kilonewton. So I got the reaction A. I don't care about reaction B. I got reaction A. If I now cut any section, I need one thing, that if I cut any section along the cable, I know that bending moment at any x is equals to 0, and based on that concept, I can get the value of y. So let's have that concept that let's take the first case. Let's cut the first section, that I would say bending moment at section that's at where the ordinate of sag is y1. So let's write that first equation. If I write s times y1 equals to bending moment at that section, so bending moment at 80 meter from A. Can we say that based on this one? If I know that what is the bending moment at this location, 80 meters, this is your only one load is there, that's the reaction A, and there is some moment mx at that location. So I can get the bending moment value at that section x. So that by this way I can say h times y1 equals to reaction of A 787.5 kilonewton into length of 80 meter. So I got the first value, and this is coming to be equals to that some value we have, but this is lesser. Let's say this is some value. Similarly, if I write h times y1, h times y2 at the second location, that at this location, when x equals to 140 meter, that means we are saying that this one at this location, we know bending moment is 0 in the cable. Bending moment is 0, and if I take that in the simply support beam by the general cable theorem, I would say hy2 equals to what's the bending moment about that section in the simply support beam? Can you say what's the bending moment about this section? And I would say that is equals to reaction A is 787.5 into length of 80 plus 6, that is 140 meter, and it's clockwise. And second one, because of the load of 300 kilonewton, and that's anti-clockwise, so you can write 300 into 60 meters. So overall value of 92250 kilonewton meter. And I would say what is the value of hy3? That's at section 3. Can you calculate that value also? hy3. So now your section is at this location. Your section is there. So I would say the bending moment at that section from the right side, I would say that is reaction A 787.5 into length of 80 plus 60, that's 260 meters, then minus effect of the load 300 and length of 120 anti-clockwise, and one more load is 150 and length is 60 meters. So that overall value is equals to 112,500. Okay, so we got different values. Now if I calculate that, the last section we have the fourth load at this location, I want to say what is the sag y4. If I write hy4 equals to bending moment about this section in the simply support beam. So if I calculate that, I would say a reaction of A, that's 787.5, and the length of 280. Length is 280. Minus effect of that load 300, and the length horizontal distance up to that point is 260 plus 80, 320. Is that 320? Yeah, 120 plus 80. That's 120 plus 80. That's 200. Length of 200 minus your 150 kilonewton, and length of 60 plus 80. That's 140. So 140. Length is 140. After that, we have one more load, that is 300 kilonewton and length of 80. So I write minus 300 into length of 80. that equals to what's that value equals to? This is 115500 kilonewton meter. So based on those values, I would say since your value of h is constant, h is not changing, so h is fixed. If the value of h is fixed, that means it does not change. It does not change. So if I have this value, let's remove that value now. If I compare only that values of y, y1, y2, y3, y4, I would say based on these values we have 92250, 112500, 115500. I would say this value is bigger with respect to the others. That means y4 is greater than all others. That means the sag developed at a location 4 where the load of 1000 kilonewton was there, the sag developed at that location is maximum. Can we say that? Can we say that? Sag developed here is maximum. I think we can say that. I think we can say that. I think we can say that. This was the end of this problem. Because h is constant, so we only have that effect of y1, y2, y3, y4. So let's go for those a bit of that we have touched it already. This is what we call as cable profiles. Cable profiles. Cable profiles. So if you have a cable and that you support freely between two supports. So let's say this was some cable, you support it freely under it. Say you would say there is no load, external load. It's under the self weight, and the profile it's formed. It's some sort of profile gets developed. That this profile under the self weight, we call it as catenary. We call it as a catenary. So under its self weight, so there is some self weight of W. So there is some self weight, we can say W self, because of the self weight under the two supports, it's taking the shape of some sort of shape, what we call as catenary shape, catenary. So that means load is along the length of the cable, along the length of the cable. When the load is along the length of the cable, this is only possible because of the dead load. Let's say because of the dead load, there might be some, because of the self weight, there is some weight, and that weight is, we say that's homogeneous for the if the cross section is same. So the profile format would be catenary, and this is not the length of, this is not the horizontal length. This is the length of the cable. That's this one. This length is the length of cable. This length we call it as S. We represent this length as S, and the horizontal length we represent that as L. Horizontal length we represent that as L. Now second is that if you apply load in the horizontal only, and the profile developed would be, let's assume that there is no self weight. Let's assume that there was no self weight, and if I say there was no self weight, the profile format is also in this way, but we call this one as parabolic profile. Parabolic profile. We would be deriving an equation for this one also. So we say if the load is along the horizontal span, we can write here load is along the horizontal span. Load along the horizontal span. Along the horizontal span. Load along horizontal span. In this one, initial one, load was along the length of the cable. So we say this is the profile format is a parabolic profile. One more thing is that we have a concept of what we have. What we say that funicular systems. These can be we say these can be cables, and these can be arches also. Arches are in this fashion, and cables are in this fashion. So cables means the funicular means they only have axial tension in the members. Axial tension is only there. There is the only system that means only axial tension is operating. Only this is the only force that's operating in the section, in the member. That's what we call the system as funicular system. Then one is that, so we already saw that to maintain that summation of forces under the point loads, cable takes those straight line segments, and under the under the what you have under the UDL, it takes the shape of it takes a smooth shape. It takes a smooth shape. And this was under point loads, straight line segments. Okay, straight line segments. So because of that flexibility. Now the thing is that let's go for the topic. Yeah, that's we have that analysis of the cables subjected to those point loads or concentrated loads. So this is the case one when the cables are subjected to concentrated loads. If I take this now, I would say let's make them a whole. I would say we have some loads. Because of that, we have a straight line segments. The few of the straight line segments have been developed. Let's say this is some support A, and there we have one more support B. And let's say this is the elevation difference. Let's call it as YB, elevation difference YB. And from this one, let's have that horizontal line. And let's go for the chord also. Let's have the chord also. This is your YB. Let's have the chord also. There's some theta. Or we can say there's some theta. And you go to some x. There we have some sag. There we have some sag of the point. You take any point P at location of x. You have some point P. So let's call this point as let's take the loads first. Let's say there's some load P1, we have load P2, and Pn, so on and so forth. And we take any point at a location of x from the support A. At that location, we say your sag with respect to the straight line. We say the sag hx, we write it as hx. We say the sag with respect to the horizontal line. This one we write it as hx. This one. One was your yc, that was with respect to the chord line. So this is your hc. So hc is the sag with respect to straight line from A. And yeah, this was your yx. This is your yx. Sorry, this is your that sag h at any x. Sorry. Y at any x. Yeah. This is what you call as this was your yc. This was your y at any x. This was your y at any x. Sag with respect to straight line from A. And one more thing is that we have small hx. This one is your hx. And this one is your hx. And there we have some this one. By the similar triangles, we say this one is your that yb per unit length of x, but I need for the length of x. Yeah. So I would say value of hx sag at any x. This is sag at any x with respect to the what you have, what you call as with respect to chord AB, and that equals to yc minus yb by L into x. Okay. So for the analysis of the cable subjected to concentrated loads, one of the critical thing is that you need to keep in your mind. That's we say that force remains constant in that segment. Force is constant. That tension force is constant in the segment. Now, based on this one, we are going for the first problem. So we have that we have three loads. We have two loads acting on the cable such that the profile gets developed in this fashion. Profile gets developed in this fashion. Here we have some load of 3 kilonewton. At this location, we have some load of 8 kilonewton, and we have some support at B. This was your support at A, and we have some B, C, D, A, B, C, D, and I would say the horizontal length between these points is, let's say this is 2 meter. This is 2 meter. This is 1.5 meter, and the elevation difference between supports is equals to 2 meter. So the elevation difference equals to 2 meter, and the sag and the sag at point D is also 2 meter. If I have that chord line, if I have that chord, I would say this value equals to 2 meter. No, not this is not the sag, sorry. So this was your 2 meter. This is your 2 meter from the support B. From with respect to this point, this is 2 meter. Okay. Now we need to get what we need to get. We need to get tension. We need to get tension in each of the segments. Tension in each of the segments. In each of the segments. So okay, that means you need to get tension in the segment AC, tension in the segment TCD, and tension in the segment what you have DB. In these three segments, we need to get the tensile force that we have. Okay, and one more thing is that you need to get that dimension of H. We call it as H. This is unknown of H. What is this value of H? We have to get. This is the related distance of that vertical distance of A and C. So this is H. We need to get the value of H also. We need to get this value of H. So how can you solve this problem? Based on one thing that we have general cable theorem that says Hy equals to bending moment at any x in the simply support beam. This is for the cable, and this is for the bending moment in the simply support beam. So this is the one result we have. So for that bending moment at any x, for that we need reaction. Let's say reaction A or reaction B. You can go from either of the side. So you need the reactions. You need to calculate the reactions. Can you calculate the reactions? Can you calculate the reactions? Let's try to write the reactions. Let's try to get the reactions. I would say here we have some horizontal reaction of H. Here we have some vertical reaction of A. Here we have some reaction of vertical B, and here we have some horizontal reaction of H. So if I write summation of moments about point B equals to 0, I can have equation of 1. I would say your H is acting clockwise about the point B. H is acting clockwise about the point B, and the distance is 2 meter. Vertical distance, that is 2 meter. H into 2 clockwise positive, plus your reaction of A into length of total length is 2 plus 2 plus 1.5. That's 5.5. 5.5, and that's also clockwise, and the effect of those point loads, that's anti-clockwise. So I would write 8 kilonewton into 1.5 minus 3 kilonewton into, that is 3.5, and that is equals to 0. Can we write this equation? Is it correct? Is it correct equation? I think it is correct equation. And if I simplify it, I would get an equation of 2H plus 5.5A. Yeah. What is the thing here? Can you tell me what is the moment of H about the point B clockwise or anti-clockwise? So your point B is here, your moment load is acting here at some eccentricity. So let's say the line of action of H is here. So if I see this point with respect to this point, it's having eccentricity in this way, that this is your 2 meter and load is in this way. So it's trying to have a anti-clockwise rotation about the point B. Can we say that it's trying to have the anti-clockwise rotation? Let's say this is some lever arm of 2 meter, and this is point B. You're applying horizontal rotation in this way, so anti-clockwise rotation. This was so such that your H into 2 is negative. Your H into 2 is negative for this case. If the point B was above, let's say this was point A and this was point B here. That means if this was 2 meter, and I would say because of the H, it's having clockwise. If I take now that about this point, if this is your point B, about this point B, you are having this direction is same. You are applying in this way load in the negative x direction, so it's having clockwise rotation. So that was positive. For this case, we have negative H into 2. So I will write minus 2H plus 5.5A. That equals to some value of 22.5 kilonewton meter. Now we need to get one more equation. We need to get one more equation in terms of H and A, such that I can solve two equations for two unknowns. if I write one more equation, that summation of Fy equals to 0, summation of Fy equals to 0, I would say A plus B, vertical reaction A plus B equals to 3 plus 8, 3 plus 8, that is equals to 11. So now if I know that, if I know the sag here, if I know the sag here, if I know the sag for this part, do I know the sag here? I know that y bar, y equals to 2 meter here for the segment D, y at D equals to 2 meter with respect to the point D. If I have the segment, you have a load of H here, you have a reaction of B here, and you have this segment D, and at this segment, because it is a it's a cable segment, here the moment is 0, here the moment is 0. That means if I write the summation of moments at the section D equals to 0, I would say H is balanced by H into 2 is balanced by reaction B into 1.5 meter. Can we say that? Because your cable is there, it is having bending moment at any section 0. If I take this part of the beam, if I take this part of the cable, I can apply that moment, summation of moments at that point D equals to 0. Do you agree with that? I think it's okay. I think it's okay to have. Now, if I write this 2h, if I write this is 2h equals to, what's the value of B we can have in terms of A? Because our first equation was in terms of A. It was in terms of A. So if I have that equation, I can say this value B equals to 11 minus A, 11 minus A, and multiply of 1.5. And accordingly, we can get one more equation, 2h plus 1.5 of A, that is 11 into 1.5. That is 11 into 1.5. 11 into 1.5, what is that value? Is that 16.5? 16.5. So we have two equations, we have two unknowns. You can go with the calculator and you can go for the equations, then go for the linear equation of between two variables, and you can get the equation. You can get the values of H and A. So your horizontal reaction, horizontal component of the tension is equals to that is equals to 4.0714 kilonewton, and A equals to 5.5714 kilonewton. And accordingly, you can get the value of B equals to 11 minus A. That was equals to 5.4286 kilonewton. So we got these three reactions. What was the unknown we had in the problem? We need to get tension in each of the segments. So once we got the reactions, let's cut the sections. We need to get the tensile force in each of the section. We need to get the tensile force in each of the section. Let's cut the first section. Let's cut the first section. That's AC. Let's have the AC. I would say here the force is horizontal equals to H, and there is some vertical reaction of A. And now you're cutting just before C. That means from this side there should be some balancing internal forces. I would say there would be some internal horizontal force. That should be equals to H. To maintain the equilibrium. And there would be some horizontal reaction along the vertical, such that is also equals to A in the opposite directions, such that the system is in equilibrium. It has to be in equilibrium. And I would say if you have the resultant of these would be in this way, along the line of the member, along the long axis of the member. So there's some resultant R that we call as tension. Let's say this is some tension of TAC. This is the that we can have that resultant of those vectors, h square plus that a square. Can we say that root of s square plus a square? Theta is 90. So we write s square plus a square. Similarly, from this side we can have this resultant. So if I write what is the value of TAC, that equals to h square 4.0714 square plus 5.5714 square, and with the root, and you can get the value of TAC. TAC is equals to 6.9, not 6.9, 6.9 kilonewton. 6.9 kilonewton. So this is the force one in the first segment of the cable. Now second segment is that if we keep it till now. If you go for the third segment from this side, that's easier. That is easier to calculate. If you go for the third segment, that's easier to calculate. Let's go for the third segment first. I would say this is the segment C, third segment that we had name of D and B. There's some horizontal H, and there's some vertical B, and there might be some resultant that we can call TDB. That is root of H square plus B square. And if I know the values of H and B, I know the values of H and B. I can write that H square value of H was equals to 4.0714 square plus value of B was equals to 5.4286 whole square. So I can get the value of TDB equals to 6.79 kilonewton. Now similarly from this side also, if you cut the section, there should be some balancing forces in the opposite direction. So this is also H, this is also B, and there's some resultant R that's also equals to TDB. So this was the second case. And third case, we need to have, you can have it from either side of the section. You can take it from either side of the section, from either side of that section. Let's take it from the left side. Let's take it from the left side. So you're cutting the section. You have to cut the section at the location of D. You have to cut the section at the location of D. If I cut the section at the location of D, that means I have to show all other members also from the other side, from either of that side. So let's have this one. I would say initially at the point A, there was some horizontal of H and there was some vertical of A, and here we have some reaction of 3 kilonewton, and we are cutting just before point D. We need to get the value of TCD. And for that we need to get, I would say, those components at this section. What is the value of H and A? What is the value of horizontal and vertical at this section? We need to get those values, and from that we can write that root of that H square plus some reaction square. And we need to do free body, that summation of forces in y direction. If I write the value of A equals to, the value of A was equals to 5.5714. This was 5.5714. See, the direction is upwards, and your one more load is vertical downwards, 3 kilonewton. That means there should be net of these two on this section to balance, such that this section is in equilibrium. Can you tell me what should be the value here? Net value. So I would say net value of A, that net value of 5.5714, it's upwards, and minus, if you subtract that 3 kilonewton, that's downwards. So net value is equals to 2.3 minus 2, that's 2.5714. That's net value of upwards. So at this section you have to take this amount of load, but that should be downwards. So I have to have this amount of force at this point downwards, 2.5714 kilonewton. And by the summation of Fx equals to 0, I can say there's only one horizontal here. That means here the reaction developed would be also H, internal force H, and there would be some resultant of that we can call as TCD. That's the root of H square plus 2.5714 square, and that equals to 4.82 kilonewton. 4.82 kilonewton. So we got the forces. We got all those three forces we had. We need to get the tension in all those segments. We got that. And one more problem was that to get that sag H, we need to get this dimension of H. What is this dimension of H? Can you get this value? Now? What is this value of H? If this is 2 meter, and this is some section C, and there's some horizontal here, there's some vertical here. If I know that equation, if I know the condition that cable is flexible, that means bending moment at any section is equals to 0. If I have that concept, I would say you cut any section. Here the bending moment at that section equals to 0, and all other loads we have, then you apply summation of moments at that section. Now you apply summation of moments at that section equals to 0. I would say we have only two reactions. One is H and one is reaction of A. And we have ordinates also, that vertical and horizontal. This is your 2 meter horizontal, and this is your this is your H unknown vertical. So this is your H. Now if I apply summation of moments at that section X, this is your X from the support A. This is value of X equals to 2 meter. Can you get the value? Can you get the value of H now, small h? We know the value of capital H and A. We know the value of H and A. I can say the value of H would be such that your H into H about this point, it's in this way. It's anti-clockwise. So I will write minus and plus effect of that point load A, concentrated point load, that reaction A. That's clockwise about the point of A into 2, that equals to 0. So I can write H into H equals to 2 into A. So I can get the value of H equals to 2 times value of reaction A, some kilonewton was that, and value of horizontal, that's also some kilonewton, and you can get the value of that horizontal, that sag at A with respect to point D. So you can have that value. That is coming to be 2.7368 meter. 2.7368 meter. This is the end of the problem. Let's go for the case 2. That's the cable is subjected to a uniformly distributed load. Cable is subjected to uniformly distributed load. So we have cables versus UDL. Now first case is that if you take that cable between the two supports such that it's having some self-weight. So if you take any strip along the length of ds, on that there is some weight of W. Similarly, on all those small ds strips, your weight is same. But if you take with respect to x, so if your x is along the horizontal, if you take any segment x, section x, there we have some segment x, small. At that location, we say the intensity is varying because you can take one of the segment in this way, one of the segment would be in this way, one of the segment would be in this way. So load would be different along the x at that value of x. So we say your intensity is some value of Wx. So if I cut that segment anywhere, if I take a part of the segment, I would say if I take the cable, if I take an element of the cable such that it's that delta x equals to almost tending to 0. So I would say dx is there. If it's very small, that delta x equals to almost tending to 0. So there might be some dy here. There might be some dy here, and it is having some intensity of wx. At this location, we have some intensity of wx, and from this side we have some shear force. We have some this one on the colors. We have some net resultant internal force of Vx. We have some Vx here. Let's say we have some Vx, and we have some horizontal H, and we know H would be same. And from this side, let's say because of this UDL, here we have some internal force of V plus dV, Vx plus dV. Now, then if I apply summation of Fv equals to 0, I would say that Vx, then UDL. If the UDL is, if this loading is very small, if the loading is small, we say we can treat it as a UDL. We can treat it as a UDL Wx for the intensity of, for the length of that small dx, delta x. So I can write this is also downwards. So I can write Vx is downwards plus intensity of Wx, and delta x, it's also downwards. That's balanced by Vx plus dV. So I can write that dV by that small dx is equals to Wx. This we already know. Okay. Then we do one thing I would say, based on this one, there would be some horizontal that tensile force at this location of x. There is some tensile force that's equals to Tx. And do you know that what is the value of the Tx? I would say that is equals to s square plus Vx square, and root of that. Now, if the segment is very small, very small, such that it forms such that we have, this is your dy, this is your dx, such that it's your dy and dx. and we have some theta. And along the direction of the member, along this member part, this is your small ds, this is your small ds. Along the line, there we have some tensile that tensile force of Tx. If I know that what is the value of Tx, I would say your Vx is in this way, your H is in this way, then I can get the value of that Tx. I would say the Tx would be in this way. And at this location, we have some small theta x. If I say what is this value of theta x, if I say what is this value of tan theta x, that we can write that's also equals to dy by dx. That's also equals to, if I say that's also equals to some shear Vx, or we can say this is the vertical component of the tensile force in the cable Vx, and divided by H. We can have this equation. 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 Now let's try to substitute this Tx in this equation. Let's try to have this equation. So if I say Tx equals to that Tx equals to h square plus, that's root of h square 1 plus Vx by h whole square. Can you say it in this way? Can we write it in this fashion, that Vx by h, this one, if we convert it in this way, I would say that T at any x is equals to h times root of 1 plus Vx by h whole square. And what is the value of Vx by h? That is dy by dx. That's dy by dx. So I can have the equation that that tension in the cable at any section x, that's h times that horizontal component into root of 1 plus dy by dx whole square. Dy by dx whole square. Then we say that if you try to expand this, when you say if you try to expand it, then we generally get a relation of that h t at any x is equals to h times 1 plus 2 times dy by dx whole square. We get it in this way. Let's keep both of those results. Let's keep both of the results as important ones. Let's keep those in the bracket, in closed curved paths. This is the results we got. Let's have those in closed systems. Now from this one we say, because this was the analysis where we said that load was along the length of the cable, along the length S, and because of that we say this profile is catenary profile. Now one thing is that once we got that dy by dx equals to dv by dx equals to wx, now one more thing is that from this one we have this one, dy by dx equals to vx by h, dy by dx equals to vx by h, and from this one we have differential of that v. So if I once more differentiate it, I would say that d2y by dx2, that's equals to that dvx by dx and 1 by h. So I can say this value is equals to wx. This value is equals to wx. So I can write, I would say d2y by dx2, that is equals to wx by h. I can write this equation in this fashion. That d2y by dx2 equals to wx by h. Now let's keep those two results. One is this one, d2y by dx2 equals to wx by h, and one more result was that t at any x is equals to h times this function. Let's study now that cable versus horizontal load, that UDL on horizontal length, L. Initial case was the study of, that was the exact study that load is along the horizontal, along the length of the cable. Now this study is that we say we are keeping only on the horizontal span. The load is only on the horizontal span. Simple, similar to that of assembly support beam having the load on the horizontal span. So for that we had to go for the analysis. We have to go for the analysis. We have that member A here, support A here, and we are applying that UDL. Because of that UDL, initially the two supports were in this fashion. If the cable was not, if the cable was not what you call as flexible, it would have been here. But because of the loads, it has deformed in this fashion. Let's say it has deformed in this fashion. It has deformed in this fashion. So because of the load on the horizontal, can you say what's the W at any x? What is the W at any x? If you take any section at x from A, what is the intensity here? Can you say that the W at any x, that's constant value? That's constant value of W naught. Along the horizontal, we say intensity is same. But in the previous problem, we say it was along the length of the cable. We say along each DS was same UDL, but along the horizontal, we say it was varying. It was varying because your that segment was varying. You take any segment, it was varying. It would have been any shape. But in this one, we take any strip that is always horizontal. That's always horizontal. You go to some x, there will take some dx. So we say for that you have intensity of W naught. You have that intensity of W naught. Now from the previous problem, if I write that equation, if I write this equation that d2y by dx2 equals to wx by h, if I write this equation that d2y by dx2 that is equals to w at any x divided by h. Now if I write that, what is the wx? I would say that this is W naught. So let's go for this equation and try to integrate it. Let's try to integrate it. So if I integrate it, I would get dy by dx, that's equals to W naught x by h plus some constant c1. And once more integrate it, I would get y equals to W naught x squared by 2h plus c1 x plus c2. Now I had to apply boundary conditions. Now because of these loads, we got this profile. That's a parabolic. We can see from the equation. We can see that it's some sort of parabolic nature. Now we want to take any point as origin. If you take any lowest point, if this point is O, that is the lowest point. That is the lowest point of this cable. Lowest point of cable. If I take this as origin, O. If I take this as origin O, then we go to some value of then we have some value of y and x here. So we go to some x from origin. At that location, we are having some value of y. So value of y is also from origin, and value of x is also from origin. So from the lowest point. So now the thing is that we have the profile format. Then we would see there is some sag of h1 of this support. Let's say from this support to the lowest point, we have some value of h1, and from the other side we have some sag of h2 on the other side of this, on the other support. We can say this is support B. Let's say this is h1 and h2, sag 1, sag 2. Then I would say the length here is L1. The length here is L1. This is L1. This is L1 up to the point O. And similarly from this side, I would say this is L2. And the total length is L. Total length along the horizontal is L. Such that L1 plus L2 equals to L. Okay, fine. Now let's apply the boundary conditions for this equation. That if I keep the origin as the lowest point of the profile, then we would see what is the boundary condition we can have. If I say at x equals to 0, that means at point O, at x equals to 0, I would say value of y. What is the value of y also? Is the value of y also 0 at that location? Because this is our reference origin. So that means your C2 is also 0. If I say value of at x equals to 0, that's at the origin. What is the slope at this location? Can you tell me what is the slope at that location? What is the slope here? Can you say the slope is also 0? That is the slope. Theta is 0. That is dy by dx. Dy by dx is also 0. Now, if I substitute that also in the first equation we have, so I would write from this one, I would say C1 is also 0. So the final profile, so the final equation of this kind, when the load was subjected to, when the what you call as, when the cable was subjected to horizontal load along the length, subjected to that load along the horizontal. So we say your profile becomes y equals to W naught x square by 2 times h. Now we got this final equation. That's a parabolic equation, parabolic. So parabolic profile we can have, parabolic profile. Now let's study it, this profile. Let's have those limits. Let's apply the limits. Now if we go, this is our positive x, this is our positive y. Let's go to positive value of x equals to L2. If you go for x equals to L2, we would say, what is the value of y2? YL2. So I would get value of YL2, that is equals to W naught some value of x square, that value of L square, L2 square by 2h, sorry. Y at L2 is equals to W naught L2 square by 2h. Can you tell me what's the value of y at L2? What is the value of y at L2? What is the ordinate of y when you go from that origin to the length of L2? At that location, we have that ordinate of h2. We have the ordinate of h2, so we can write that is equals to h2. So finally, I would say the horizontal reaction, horizontal component of the tensile force in the cable, that's equals to W naught L2 square by 2 times h. So you got the first equation for the horizontal. Similarly, if you go for x equals to minus times L1, that means if you go from this side, x equals to minus L1, we want to say what's the value here we can have at x equals to minus L1. Now, second thing is that if you go for x equals to minus times L1, at that location we have some value of YL1, but that is equals to H1. Is that equals to H1? Is that y equals to H1 at that location? At that location we have some value of Y1. YL1, that's equals to H1. So based on that, if I substitute those values, I would say H1 equals to W naught this L1 square by 2h, and I can also get that horizontal h equals to W naught L1 square by 2h1. Yeah, this was your small h. So this was your small h. This was your small h times h2. So this was your W naught L2 square by 2h2. Similarly from this one, so if I equate these two, we can get the result that we can solve for the horizontal reaction, that is also equals to W naught L1 square by 2h1, and that's also equals to W naught L2 square by 2h2. So you got the component of that horizontal component. Now from this one, can you got one relation between those L and H? I would say L1 square by H1 equals to L2 square by H2. And from that, I can say L1 by L2 equals to root of H1 by H2. So keep that also in the copy, L1 by L2, H1 by H2, yeah, root of. Now we got the horizontal component, but we need the tensile force, that maximum tension we can have. That is that tension maximum, Tmax is equals to H square plus reaction square. So we need the reaction also. But we have already converted the equation in terms of that reaction at any section x. We had the equation for that. So we can keep that. If I use that equation, h times 1 plus dy by dx whole square. H times 1 plus x dy by dx whole square. So for that, for this case, it's a unsymmetric profile. Your cable is in the form of unsymmetric profile. Your profile is a general profile. That means when the two supports are different levels, we call this cable as unsymmetrical cable profile. So for that, we directly go for the Tmax. That's h square plus reaction square. That's S square plus reaction square. So you need to get the reaction at that particular section, and you can get the T at that location. So one more thing is that we have, can you get the value of L1 and can you get the value of this? What should be this value? Where is the lowest point of the, what